Ready, howdy. How are we doing today, everyone? Good. Awesome. Sorry for the little delay. I just wanted to make sure I have the Zoom recording up and ready to go. So if you need to, I'll post this afterwards. And then you should be able to go back and watch it. And then if you have any friends that aren't here right now, they should be able to watch this afterwards. Hey, how are we feeling for Friday? Thumbs up, thumbs down, thumbs down. Okay. What would we like to do today? I know last reviews or like 2 weeks ago before the exam, we kind of went through the homework. Is that something we want to do again? Head nod, yes. Okay. Kind of similar thing where we just kind of go through, work it together, and then talk about it along the way. Does that sound work for everyone? Okay, awesome. I'm gonna try and use my iPad, I think, and then that should display up here. But if I need to use the whiteboard, I can do that as well. Alrighty. So our first question is osmosis is the process in which solvent molecules move through a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. What do we think for this one? True. I heard true and false. What would make it true?
It's higher, lower.
What do you think?
It's the thing that makes why it's true. What are you asking?
Yep. Why is it true?
So suppose we have two like liquids. So one is like an aqueous solution with salt, lots of salt, and the other is like distilled water, and we have a membrane between them. Salt can't go through, but the water can go through. So what the water does, let's say we have a lot of it also, of course it flows through from the distilled water flows through to reduce to dilute the highly salt-containing water.
Yes. Okay. Yep. So the answer is true here. What is happening is we have a container like this where we have the membrane in between them, right? We have a lot of high concentration on this side and then lower concentration on this side. In order to balance out those concentrations, the water will flow to the higher concentration in order to dilute that higher concentration. Okay, it's going to dilute this side while removing water from the other side, almost increasing that concentration. Does that make sense what's happening? Okay, so the water is the only thing that can flow through that membrane, like the student said up front. And so in order to make this true, the water has to be able to flow from that lower concentration to higher concentration. Okay, good on that one. Yes. Right, we kind of think of diffusion as like it's starting and dispersing outwards. This is kind of similar to this, where the water is the one that is dispersing to the higher concentration. Okay. Question 2. Consider the two reactions. We have these here, both with a heat of reaction or that delta H. What is that delta H called?
Enthalpy.
Yep, this is your enthalpy. Okay, we want to know what is the enthalpy change for the reaction. So what is this asking us to do? What do we need to do, or how do we solve this type of question? Yeah, we have to cancel the stuff out. We have to look at our overall equation and look at the steps in order to get there and rearrange them to figure out, once we add those two steps together, how do we get to that final chemical equation? So in order to solve these, I always use my final chemical reaction as like my starting point. So I look and I see I have KBr solid. It's only solid as a reactant. So I have to look at the steps given to me and see, where is this a reactant? Where is it a reactant? Or where is that KBr solid in your two equations? The first or second one? The first one, right? We need it to be a reactant in the last one. Where is it right now? It's on the product side. So what are we going to do in order to make this product here a reactant? What do we have to do to this? We have to flip it, right? We have to flip this reaction. So that makes this now KBr solid equaling K plus gas plus Br minus gas. What does that do to the enthalpy of reaction? It makes it positive, right? If we're going to flip this, that says that we're negating it, we're doing the reverse reaction. In the forward reaction, it's negative 682. In the opposite direction, it's 682, positive 682. So this is 682 kilojoules per mole. Following so far? Any questions? Okay. Is there anything else we need to do to that KBr solid in order to make it match the final situation that's in? Or does it look good?
Yeah, to find until we change the code H2O. That's
Not yet. Not yet, right? So just looking at the KBr solid, that looks fine, right? There's no extra coefficient on it. There's nothing else. It's on the reactant side. It has a coefficient of 1. That's good to go. We don't need to touch that first equation again. Now we need to look at I would look at my 12H2O next. Okay. Where is that as a reactant or product in the second equation? It looks like a reactant. Do we need to change anything to that second equation to make our overall equation look the same? No, right? That looks good to go. So we can take your KBr solid and we have our second equation. And if we were to add those two together, what cancels out?
Stuff that exists like in both.
The stuff that exists on both the reactant and the product side. So that here is your K plus gas and your Br minus gas. We add those two together and we get KBr solid, 12H2O, K plus aqueous, and Br minus aqueous. Does that match the reaction that we're trying to solve for? Yes. So what do we do to our enthalpies in order to find what this enthalpy is?
Add them up.
Yes. Right, we can take 682 kilojoules per mole plus minus 657 kilojoules per mole. And what do we get as an overall answer? Yep, you get positive 25 kilojoules per mole, which is B. Yep. Yep. I always look at it as like how to manipulate the equations. But you just want to make sure that whatever it adds up to at the very end, you can match it there. Yep. Any other questions on 2? Do we feel comfortable with 2? If you're given a third, like, yes, go ahead. In terms of, so reaction 2 has a negative 657. So you just want to make sure you hold on to your positive or negatives depending on if you have to flip an equation or if you have to like multiply or divide. If we have to multiply a whole reaction by, let's say, 2, what do you have to do to its enthalpy? Also multiply it by 2. If you divide by 2, what do you have to do? Also divide by 2, okay? So whatever you do to that chemical equation, you also do to your enthalpy of reaction. If there's 3 equations, don't be scared. Just make sure you're looking at what needs to be a product at the very end and what needs to be a reactant at the very end. And you should be able to add your equations to get to the correct answer. Any questions at all? Question 3. We have for the reaction, given there, the change in the concentration of H2O with time equals the rate of reaction.
And this is supposed to be used.
Yep, so this is just what do we think? Is this true or false? Why is it false?
Or geometric ratio must be observed, and that would say that for the rate of reaction.
So how do you define the rate of reaction? So rate of reaction is d concentration of X over dt. And can we actually determine what dx over dt is?
No.
No, we can't actually find what this is, so we have to use the reactants or products instead. So what else is dx over dt equal to?
Concentration of CH4 over dt, or otherwise like
What do we have to do to that CH4? Make it negative because it's a what? A reactant. All of our reactants will always be negative. So what does that mean for H2O? What would that be equal to? Would H2O be positive or negative? It would be positive. So it's just going to be D concentration of H2O over what? 2 dt. Right, there's a 2 in front of that H2O, so we need to use its reciprocal, which is 1/2, and multiply our whole rate of reaction by that coefficient.
Always like it seems like a 1 coefficient.
Yes, yep, your rate of reaction will always have a 1 coefficient.
So that's right, like
Mhm.
It's just like 4.
Right, so if there was a 3, right, if it was 3 CO2, it would be D CO2 over 3 dt, right? You're just going to take the opposite or the reciprocal of whatever the coefficient is in front. Yes.
Why did you
We can. I just didn't write down all of them. Yep. I just was using it as a reactant or product example. Yep. So, right, we're saying that the change in concentration of H2O with time equals the rate of reaction. Is that true or false? It's false because it's 1/2, right? The rate of reaction. So this is going to be false.
You're saying the rate of appearance of H2O is 1/2 the rate of reaction,
Yes. Yep.
not the other way around.
Yep. Yep. Right. So in order for the rate of reaction to equal the dH over dt, we have to multiply that dH over dt by 1/2. Okay, and that's why it's false. Go ahead.
So the question was, what the change in concentration of CH4 over time?
Yes. Yep. So if we change this to, I guess technically not CH4 because then it would be negative. So if we said CO2, then this would become a true statement. Yes.
So you said, sorry, if it was concentration of half of CO2, then it would be correct?
If it was concentration of CO2. Right.
Half of H2O?
Yes.
Okay.
Yep.
That's false because that 2 coefficient.
Yeah, because of that 2 coefficient. Do we understand why it's false? Yes. Okay. Do you understand what would make it a true statement? Yes. Okay. Any other questions on question 3? Yes. I could have done that. I just picked one that didn't have a coefficient to show the difference. Yeah. Okay. Question 4. If the rate law expression for reaction where rate is equal to KCH4 times O2, the rate could have units of millimolar, over seconds. True or false? True. Good. And why is that true? Yep. So if we have, what order is CH4 here? Yep, this is first order. What is O2? First order. Okay, so we're multiplying two concentrations, so we'll have some sort of concentration squared. And then we always need to have a unit of time to be below our, in our denominator. So in order to make our rate constant cancel out, right now, I would have a different unit here, but always your rate, which is, oh, not this. The rate that we're looking for here will always have units of concentration over some sort of unit time. Okay. Your lowercase k here will have the units to cancel out those two concentrations that you're multiplying on top in order to get you to one concentration on the top. What would be your units for k here? I heard 1 over. Millimolar times second.
And the overall order of the reaction was just like multiplying the next one, right?
We're adding the exponents together. Yep. So we have 1 plus 1 is 2. If we had if you had 1 first order and 1 second order, that would be 1 plus 2. So overall is 3.
So why do we have the millimolar, like the first order thing?
Yep. So that's just right. We're just saying that we have 2 orders. It doesn't really matter what those orders are because we're just asking for the rate. And the rate will always have concentrations of concentration over time.
Oh, so about
Yep, it doesn't really matter on the order. If you're trying to find the units of K, that's where the order matters. Question? Yeah.
Yes, why is it 1 over, like, why is that not, why would it be true that the rate of reaction?
This one here.
Yeah.
So that would be what the units of K are. So if he asks you a question like the units of K are 1 over, right now it's asking just for the rate. So it's asking for capital R. Yep. Yep.
Yeah, he said in class, the rate of reaction.
Yep.
If the overall rate.
Yes.
Yeah, he was like, he said, you see it on the exam.
No.
No, I just don't.
So that's a good question. The rate constant. Yes.
This matches this answer.
Okay. So if we had a reaction where it was R is equal to K CH4 times O2, right? The one given here. Our units for R is what we said was millimolar over seconds. And then our units for K would be 1 over millimolar times second. Right? This is what the question is asking for up here. All right, we're looking for units of R, millimolars per second. It's true. If we had R is equal to K CH4 O2 squared, what are our units for R? It's still millimolar over second.
Because the goal is.
because units for K
Okay, so just like,
would be what? 1 over millimolar squared times second. Right, so K is the unit that's changing, R is not changing. Yes,
I don't think I understand, so did we explain how you got 4 again?
how I got
4, like, why you know it's true?
true, because your units of R will always be 1 concentration unit over 1 time unit. Okay, so it doesn't matter what the order of anything is right now, it doesn't matter what this rate equation looks like. It just matters that it's a concentration unit over a time unit.
The fact that it's millimolar.
Doesn't matter. Nope, it could be millimolar, it could be micromolar, it could just be molar, it just needs some sort of concentration unit. Yes. Yep, so. You got it, Okay. Right, this would be an overall order of 3, this would be overall order of 2. Okay. Any other questions on this one? Does this make sense why it's true for 4? Yes.
So it's always true because, R is always gonna be like concentration over time.
Yep, the thing that's changing is K for your units, R units doesn't change.
Okay, so that's what like say is gonna be.
Yes, that would become a different question. Yep, yes. So for this one here, we have, what's our overall order for this second one? Help her out, what's the overall order? 3, right? And why, how did we get that? We added our 1 exponent from CH4 and our 2 exponent from O2. So 2 plus 1 is equal to 3, which is our overall order. Our units of K will always be 1 less than the overall order. And so in order to get to this millimolar over second, we would have millimolar times millimolar times millimolar, which is millimolar cubed. And so in order to get rid of that 2 extra millimolars, we need to divide by millimolar squared. Yes.
Could you give an example of like a false one?
For this one?
Yeah.
Yep.
Because I was like, I have 3 part of that, and I have 17. And I have to my school, like, you're still
Right, so here, the rate law expression for reaction where R is equal to K CH4 times O2, the rate could have units of millimolar squared per second. No, right? Because K is going to work its magic and change its unit in order to make this millimolar over seconds. Okay, so this one is false. See how one little exponent can change to a whole question?
You're right. Could it say rate concentration? As far as the same thing.
As rate concentration, it would most likely just say rate.
It's only rate and then rate constant.
Yeah. Right, we could make this false even more and put rate constant in here. And that would still be false because we're looking for this big constant or this word. Okay, any more questions on 4? Alrighty. Question 5. For extremely fast reactions, activation energies can be negative. False. Why is that false?
You can't like get like energy back. It's like a light bulb giving energy back to you, but other reducing light, it doesn't work.
So there will always be some sort of hump you have to get over in order for the activation or in order for the reaction to happen. Ledge just came from. So if we look at here, if we look at an activation curve, right, it could start off as reactants and products here. We'll make that different. Reactants and then products, right? A catalyst might happen where we then have your reactant still here, but then we go through 2 other little humps and that get us over to here, right? Something like that, right? So your activation energy will always be positive. It can never be negative. We can't go this way. It just doesn't work like that. Yes.
So like, the whole like extremely fast reaction participant goes on, it's like, there's like music.
Yep. So he's just saying for extremely fast reactions, an extremely fast reaction would just have a very, very low activation energy, right? It might look like, if we have reactants and products, it might just look like, right? It's a little hump, but there's something there that you have to go over. So extremely fast, this doesn't matter. So who can write me a true statement for this one?
In all reactions, at least some activation energy.
Right, so we could say for all reactions, activation energy is positive. Right? True or false? True. Yes.
So with the activation energy graduated, what else was like that? Like, what is it like ending higher up instead of lower?
Yep. So if your reactants here and then your products are up here, does anyone know what kind of reaction this is? It's endothermic, right? The energy is required in order for the reaction to proceed. So this is an endothermic reaction. What about this one here where we have reactants? Yes. This is an exothermic.
So is that the exothermic reacting extremely fast?
No.
Because otherwise it would burn stuff like extreme.
Yep. So, but what can you make an exothermic? So how can we make a true statement about exothermic reactions? Right? True or false? Exothermic reactions always release energy.
Yeah.
True, right? Exothermic reactions will always release energy. Endothermic reactions will always take in energy. Yes.
The graph is saying how much energy is in the system at that point in time?
So the graph is telling you how much energy is required to get to that step. So we're going to start at a lower energy and reach a higher energy. So in order, the activation energy will go over that that final energy required, and then you'll fall back down to the products. Yes. Yep. So in order for the reaction to happen, the reactants need to have that amount of energy in order for like the collisions and everything to happen properly. Yep. Yes. Yes. So when it's going up, it's endo. When it's coming down, it's exo. But overall, it is endothermic because we end up at a higher. Yep. There are always like endo and exothermic reactions happening. It's just at the very end, you can add them all up and decide. Any other questions? Okay. So this one looks weird on my,
Oh, wow.
All the like,
yeah, all these look weird. I think it's like 1.5.
okay. I think it's what I'm saying, is the A, accent, I'm gonna press the arrow over. Did you answer? No, like. No.
I think it's because it uploaded it, yeah, and this is a word document, not a PDF. So whenever you download it, whatever, like, text processor is on it.
Oh, that's why. Hours, I see.
Even it looks like.
I think it's where X.
Like, it wasn't even the first. Like, it froze, like, yeah.
Gotta be quite thorough.
Okay. So for question 6, we had in the rate of the reaction, 2A plus B goes to 2C. How is the rate of reaction technically defined? Right, so we're saying it's going to be the rate of the reaction is always defined as dx over dt. Right, that's always the rate of the reaction. Is that an answer here? No, so it's going to be none of the above. Yes.
So the piece like doing all the, like, take the, like. EA over all that stuff.
Yep.
Is just, and we just get.
Pretty much. Right, and so you might think, did anyone pick A for this?
That was.
Right, A was one of the possibilities that I considered. But it's not technically defined as it, right? The word technically here is what's going to throw you to question or to answer choice E, because it's technically defined as the dx over dt. It's approximate enough to be 1/2 dA over dt where we can use it, but it's technically defined as dx over dt. Yes.
Actually, suppose if you want to have, like the base definition.
Yes, base definition is rate of reaction is dx over dt. Yeah, they're pretty tricky.
He made like an offhand comment in class, like, this is what it is, guys. This is what it is. See on the exam.
Yep. Right, so rate of reaction will always be dx over dt, but we can use those approximations of concentration because they're close enough to what the actual answer is. Everyone understand why it's E and not A? He said skip 8 and 9, right? No, I like 8 and 9. I like that. Okay. For question 7, which of the following statements about chemical kinetics are true? Okay, so we're gonna go through 1, 2, and 3. We're gonna say if it's true or false. So for question 1, the rate of a first order reaction will change with time. Is that true or false? It's true. Why is it true?
Because that's
What do you say? Yep, time is in the equation. It also, does anyone know what a first order reaction looks like a graph? Say it again.
It's just a straight line.
Once we manipulate it, yes. But what does the non-manipulated graph look like? Just like whoop. Right, it's an logarithmic one, right? That's what I'm thinking of. Right, it's logarithmic, gonna decrease in time, right? If we think about half-life, right, that rate will decrease over time. Right, but the rate of a first order reaction will change with time. This is true. We can manipulate that equation in order to get to a straight line curve. And we'll talk about that in a little bit. Ready, question 2. The rate of a first order reaction will change with time at the same temperature. True or false? False. Why is it false? Say it again. Yep, at the same time point, your reaction will stay the same. Question 3, the overall of a rate law expression is reliably obtained by adding the coefficients of all reactions in the balanced stoichiometric equation. False. Good. Right? How do we get the overall order of a reaction? Right? We need the exponents of the rate law. Bless you. Bless you. Does anyone know when we can use the coefficients?
So,
Hold on, let me look to see if you got that.
so like approximated, the rates.
It didn't get that far. Don't answer my question. Never mind. Yeah, you'll talk about that next. You can use the coefficients in the slow step of a reaction, but you didn't get that far. Okay, so this is also false, so our answer is C. Okay, but for right now, what you need to know is that the only way that you can get the overall order of the reaction is from the adding the exponents of your rate law equation, or by solving it experimentally. And then again, adding the exponents. Any questions on 7? Yes. Yep, so we could have something where it was like 2A plus B goes to C plus D. Okay, but our rate law could look like this.
Oh, okay, so like the number.
Yep, so the coefficients in front does not match the exponent. And so we can't rely on just the exponents. We have to know, or we can't rely on just the coefficients. We have to know the rate law. Yep. What's the order for A here?
0.
0. A here,
That's not a 200 rate thing.
Right. It's because it doesn't appear in our overall rate law, but it's in our reactant side. It has a rate law, or it has a rate order of 0. What is B? What order?
Second order.
Is 2, second order.
No, order is 2.
Right, so our overall order would be 2. Questions? Yes.
So on question 4, both first the reactions were like first order.
Mhm.
Are we going to add the exponents would be like second order?
So the overall would be 2.
Okay, so. Okay, the question was on because the rates. The
Because-
order takes-
Yes, yep. Go ahead.
I'm still not sure what the difference on the number 2 is, where it's the first order we change the final. How's that different?
So, yes, the rate constant is going to change depending on the temperature that you're at. So if it,
So the rate constant never changes.
the rate constant never changes. Yes, yep,
It's a constant.
yes.
Yeah.
No, you're fine.
If the A was on the product side, it would still be a second overall rate order. Because the coefficients don't matter. So then it would just be relying on that one product. Are you okay? Does that make sense? No? Right, the 2A here doesn't really matter. It's just saying that has, depending on whatever concentration that's at, it will always react the same speed. Right, it could have a bajillion moles of A, or it can have 1 mole of A, and the reaction will still proceed at the same rate, is all it's saying there. You could, but it's convention to take it out. Yes,
So the rate, they're saying it's only dependent on,
yes.
but it shows A in there. Like, how does that logically work?
So it's just saying that the concentration of that thing doesn't matter, so it's mostly dependent on what your concentration of B is. Do I have an example of what that is? No. But you just have to think about it where you could have a whole bunch of A and a little B, or you can have a little bit of A and a lot of B, and the rates of those two things will be the same in both scenarios.
Would you be giving something like this, where it's gonna, it wouldn't normally include A or something?
I don't think that I don't know what kind of questions he'll ask, but the only way that I would see it like this is if he's trying to have you solve for the overall rate law experimentally, and you find that A is a 0th order reaction.
Can you like do the rate law stuff for B for A to be 0?
Yes, yep. Yeah. Any other questions on my little side comment here? Yes,
All the order reactions will change with time.
yes, yep. 0th order will not. Yeah. Bless you. And what, can someone tell me why 0th order reaction will not change with time?
It's in the center.
Right, it's independent of the concentration. So, right, 0th order means concentration does not matter. So as you go through a first or second order reaction, you're using up that concentration. So that concentration of your reactant is decreasing. So less collisions are happening in order for your reaction to proceed to products. With 0th order, it doesn't matter if you have a lot or a little. So it doesn't matter that as time goes on, that concentration of that 0th order thing is decreasing because it didn't matter to begin with. And so that rate will still keep happening the same way.
It's just not reacting, well. Like, right?
It'll still be reacting, it just will proceed at the same rate.
So it just adjusts
Yep, it just adjusts.
within like reasonable limits, I guess,
Yep.
like if like. So you guys do probably have to go like really small and concentration, really high for it to change at all.
Yes, yep. Do you have a question?
If the concentration of something of a 0th order reaction doesn't matter, why is it there?
Because we're chemists and we give you stuff you don't need.
So it depends like a full explanation. of it.
Yes.
Zero.
Yes. Yes, yep. Any other questions? It's just really good we're thinking like this. I think it helps you later. Okay, 8 and 9 we're skipping. Okay, question 10, another doozy. Let me write this out again. Everyone okay so far, right? I'm not super confusing anyone. Feel better so far? Yes, okay. Please speak up if you're not. Alrighty, for question 10, we have the decomposition of dinitrogen peroxide to NO2 and O2 is that reaction that I wrote in purple. Was studied at 25 degrees Celsius, and here's the table of your trials. And this is just 0.95 times 10 to the negative 5. That's all that that's supposed to look like. It's always times 10 to the negative 5. Alrighty, so what do we do to solve this type of problem? Right, so we're going to experimentally determine what the rate of this reaction is, or like your order of this reaction for this. So you're going to set up 2 different rate laws. They will both have the same setup here, where it'll be rate is equal to the rate constant times the concentration to some power. Okay, do we know what the rate would be for one of these reactions? Are we given rates? Yes, we're given rates. Are we given K? No. Does that matter? No. Are we given concentrations of N2O5? Yes. Are we given M? No, that's what we're solving for. Okay, so we can say overall it'll look like rate 2 is equal to K times N2O5, whatever 2 is, over M, and then rate 1 is equal to K times N2O5 1 to the M, right? You're going to pick two different trials, the concentration from that trial and the rate from that trial. Which ones do we want to use? And does it matter? It doesn't matter which two you use.
Because they're the same reaction.
1 and 2? Okay. Should we put 2 on top or 1 on top? You should put 2. One thing you'll know is that, or one thing you can try and look for is which one is going to be the bigger rate and which one's going to be the bigger concentration. That just gives you whole numbers, or at least like you would get an integer of like 2 or 4, right? Something like that instead of like 1/2 or 1/4. So we can do 1 and 2. So we have 1.23. K, we don't know, and we actually don't care about it. And then, I'm sorry, this is not 1.23. This is 1.20 times 10 to the negative 5. This is 1.23 to the M. And then 1 is going to be 0.95 times 10 to the negative 5. K, 0.92, and M. So when we divide these two, what can we cancel out? We can cancel out the K's. We cannot cancel out the M's. But we can combine 1.23 and 0.92 into one fraction because they're under the same exponent. So we can do whatever the math is for so I got 1.2632 is equal to 1.23 over 0.92 to the M, right? So now you can then divide those two. What do we do from here? Say it again. Yep, so you want to determine the ratio between the two. You can also solve this using your log base 10. If it's close enough where you have like 1.3 and then 1.33, you might be able to see that it's going to be a reaction, or an M to is equal to 1, right? Or if it's 2 to the 2M, then you can kind of see that it's 2. Or sorry, then you can see that the M would be 1. But if you can't tell based off of these numbers here, you can always do a log. So you can say log 10 here. You just do log and log. Your log math happens so that now this becomes log of 1.2632 is equal to M times the log of 1.34. All right, so M now becomes in the front, and then you can divide by the log. Right, we get into exponent math and log math and ln math. So now this becomes the log of 1.2632 over 1.34 is equal to M. And then you can plug that into your calculator.
No, base 10 or right?
It's assumed base 10, but you don't
Yeah,
like you don't have to plug that into your
That's
calculator.
all.
Yep.
Without including base 10.
Yep. Then you can do log of 1.2632 divided by 1.34.
Yeah, well, it's the log of.
Since this is pretty close. If you just used your rounding error, rounding math, you could probably say. This is 1.3 is equal to 1.3 to the m, and then you can say m is equal to 1. That would be first. Yes. Yep. Yes.
Can you just, since we only have 0, 1, and 2, can you just plug in that for n?
Yeah, you can also do that. Yep.
So if it were to be 0 order, it would just give you 1.3, so if you want.
Yes. Yep. So if it was 0th order, then your rates would divide out to 1.
What if it was 1?
If it was 1 equals 1, well, I would pick a different second reaction rate to see if your concentration is changing. Yeah.
So will it plug in like the options into M?
So you can plug them in where you have like 1.23 divided by 0.92 to the m. You can plug in m there.
And
Right.
see if it's close enough.
And see if it's close enough, right? What times what gets you to that 1.26?
So if you like solve for 1, you got 1.3, that's equal to M is close enough for 1.
Yes. Yep.
How do which two trials you use?
Nope.
Like, how do
You could have used 5 and 1, 4 and 1, 3 and 1, 2 and 5, 4 and 5, doesn't matter.
Okay.
In class, Dr. Lindahl told us that if we could find like, if the rates are like multiplied by a constant, then it's first order, if it's.
Yes. Yep. So
higher, it's second.
yep, that's a good thing as well. Let me just add a page. So one thing you can also look for, right? If you have 0.9, sorry, if you had 0.92 and you had 2.00, right? This is pretty close to 1. This is pretty close to 2. So when we multiply from here to here, we want to know what the rate happens. And we have 0.95 times 10 to the negative 5 and 2.10 times 10 to the negative 5. Right? Again, this is pretty close to 1 times 10 to the negative 5 and 2 times 10 to the negative 5. So we multiplied this by 2. If you increase your concentration by 2 and your rate doubles by 2, what kind of order do you have? You have first order.
So then you have to check for both your, like the initial and the concentration.
Yep. All right, go ahead. Let me check my math again. Yeah, I got a weird number when I just plugged it in real quick. Let me check my original math.
I had a notebook like that last semester. If I ever had, like, if I had to do after math, it's still not, and then I'll figure it out.
So I did.
Now I've gotten to where if I did any homework or math stuff, I just put it on the same page to find it. I had this where I like what happened.
Why?
And before that, I had like a very old, like, Apple pencil for already around back then, but like only for like I think at the time. So like,
I'm sorry. I copied that down wrong. This is 12.63. So it should be the log of 12.632. So if you change this to 12.63, then you get m is equal to 0.97, which then can go to m is equal to 1. Yep. If it was 0th order, then your rates would divide out to 1, because anything to the power, right? If it's to the power of 0, then it would be 1, so your rate has to equal 1. Is there another question? Yeah.
So there's two ways to kind of, I think this will.
Yes. Yes. Yep. Yes, so, right, for this question here, we used trial 2 and trial 1. When I did this myself over the weekend, right, I picked trial 4 with the 2 and trial 2 with the 1.23. So if you I got to the same thing where x was about equal to 1.1. So it doesn't really matter what trials you pick. He's saying that it'll always come out to that same order. Does that make sense a little bit there? So a way that you can check your answers by like plugging it in and seeing if you get a similar rate, which I think I did here, right? So I plugged in I plugged in what I knew, left a rate out, and see if I got a similar rate to what was in the table using m is equal to 1. And then I got something pretty close to it. Yeah. Probably, yeah. Any questions on 10? Does that make a little bit more sense on how to do them? If you have multiple trials, if you have multiple reactants, just make sure you're comparing stuff that where one reactant is staying constant and one reactant is changing, because if you have two things changing, they can't cancel out. If the concentrations are staying the same for one reactant, then they cancel out to 1. I think there's something like that on your practice exam, so. Okay, any questions at all? Are you bored with me yet? Okay. Oh, 4 was his name. This one. Okay. Question 11. So we have ammonium cyanate rearranges in water to give urea in this weird reaction that looks weird on my paper. So we want to use the data in the following table to determine the order dependence of ammonium cyanate in the reaction and find the rate constant associated with this reaction. How did someone solve this one? That's good. Does anyone have any ideas how we can try and determine if it's first or second order? Yeah, we can graph it. So one thing that we can do.
But we need to know when it is depleted first to know when it's like half the concentration.
That would just be mostly for half-life, I think.
But we can't like double the rate in months.
Yes.
Because they're only like running, we're not giving anything up.
Yes.
To determine like the rate from it's running down. So in order to know when, we just need to like determine that. So I guess the graph would provide.
Yep. So I graphed this first. It's a little bit hard because we have like weird, and then I wanted
They really take that long.
some organic reactions take days.
It's used to like have reaction. Yeah, I mean, in the research that you can, there's something that like Kathy's does, like sitting around. Yeah. Especially with them now. can imagine for some people like this would be like. Now when these doesn't happen, out there.
Okay, questions on how we graphed it? So I graphed it here. Does anyone know what this kind of looks like? Yeah, kind of looks like a natural log graph. What is this? I don't know what a second order one looks like. Okay, so if we look at, this would be your concentration. And this is time. I'm going to show your notes. Am I? Yes, I am. So if we look at your module 2, so we look at this here. If we're looking at a first order reaction, right, for concentration over time, we're going to have a little decrease and then it's going to slowly level out. And then your straight line plot would be ln over of your concentrations. Okay. Does ours look like this? It might. Does it also look like this one? Yes, right? So the thing between a first order reaction and a second order reaction is that first initial fall in your concentration, I would say. And then kind of like that last little dip at the very end as well. So if we're looking at it, right, our first order is going to have a little bit more of a steady slope like this. Or I can draw it right on here too, right? It'll be a little bit more like this, where our second order is going to drop and then come out. Yes. Right, so your second order is going to drop more severely in the beginning and then level out, where your first order is going to have more of a steady decrease over time.
So what's the one over 18? Wait, which one is first order?
So this is second order. This one's first.
What's the one below it? The graph below it?
That's the straight line plot of the second. Don't worry about the one below it right now. We're just looking at this first one.
Should we focus negative below?
Yes,
Oh, no, ln one is to be honest.
yes. Okay, so knowing this, what does ours look like? This looks like a second order. Why is the second order going to decrease faster in its concentration than your first order? It's more dependent on the concentration, right? The quicker it's happening, the faster that concentration is going to decrease because it's two orders dependent on that concentration.
So at least if you graph some of this.
I would be able to graph something similar to this on the exam.
So the graph more.
Yep, if it drops more, it's going to be a second order. If it has more of that steady decline, then it's going to be a first order. Yes.
You can't use like alternate versions, right, of like where you inverse the data if you use
Yep.
that's natural log.
Yep, absolutely. If it was a 0th order, let me see if I can draw it. I think it's concentration over time. So it kind of it just decreases at a straight line because it's not changing in rate at all. Okay, so we have determined that this is now second. Go ahead.
Just to clarify, like, On the graph was like straight line, we don't have to manipulate like more of a wave.
Yes, if it's a straight line, you either have to see that it's a concentration and time dependent, and then it would be 0th order. But if it's ln or 1/AT, then it would be a manipulated equation. Okay, so we determined that this is going to be second. So what is the, I guess, equation for a second order reaction? Yep. Do we know? Yeah.
So like there's the reaction equation, the integrated equation.
Yes.
How do you know when you use what? If you're not asking for rate, you just want to know like the concentration of something. You use it.
Yes. Yep. If you're asking to solve for time or a rate constant from a known given reaction, or from a known like order of reaction, then you want to use your integrated rate laws.
So if you want to solve for time or what else,
Like your rate constant or some sort of other later concentration.
then you use the.
Then you use this integrated rate law. Yep.
How do I solve for the rate?
So that would be K here.
Oh.
Yep. It's still, the K is still the same as like the rate law K. You're just using it in a different sense here. So we know AT and we know A0. So let me just. All right, so now we can say that AT, we doesn't matter, just has to pick that time. We can call that 600, right? We can say that this is 0.114. Our K is what we don't know. Our time is 600. And our A0 is 0.458. Okay, and then it just becomes solving for X here. Okay, so when you plug that into your calculator, you get the 0.0198, which would round to 0.011.
So what's graphing a reaction is like, it's kind of a straight line, but it's not a drop in its first order. But if there's a clear drop, then it kind of like evens out in second order.
Yes.
And if it's a fully clear line, it's 0.
Yes. Yep.
Reason is because, I mean, at international CAS, what you need to raise the number E2 to get a certain number. So, and because negative exponents cause it to become a fraction, it causes smaller numbers because it.
Yes. Yep. So in order to solve for K, you just need to pick a time that you're using and a concentration. So I just decided to pick 600 because it was the biggest number. But you could have picked the 45, you could have picked the 230. It doesn't matter what number you picked for your time. You just want to make sure you use that associated concentration for that time. One thing that you have to use is that 0.458 as your T0 or as your 0 concentration. No, because we have a second order, so K will always be 1/1.
But you said you can also take over the y-axis and do like ln up and then 1/.
Mhm. Yep. Yep, so you could also, right, you could graph this also where you manipulate it, so you could. Right, you could say ln of 0.458 and get a number, or you could get 1/0.458 and get a number, and do all of those to find which one gives you a straight line plot. Yep, yep. So by the time you got to the 1/0.458, then you would say, okay, this one's gonna be straight line. So your y-axis will always be concentration. You would have to do it for all of them, all time points. So starting with the initial and going to that 600. Yep.
Oh, good.
Yes. Yep. All right, so you would come up with an XY column of 0 in concentration, 0 of ln concentration, 0 and 1/. Concentration. Yep. Right, because you might look at that curve that you make and you're like, could be log, could be not. And so then you have to do the next function. Yep. It would confirm that it's first or second. Yep. So if you did, right, if you took the ln of all of those numbers, right, it's much easier to do this in Excel, which you'll like you do in Gen Chem Lab. But if you did all of that and found the ln, you could graph that just like on your scratch paper and then be like, not really a straight line, and then you could do the 1/. If you get to, right, if you do concentration over this, not straight line, you get, and then you do the 1/, and it's not straight line, probably best bet is the second order. So you probably don't have to like do the 1/, all of them, but if you have time, then you can go back and check it.
Is there a reason you think 60?
No, it's just the biggest. Seemed like the most round answer. Could have used any of them. Yep. Yeah. Any other questions on 11? Does this make sense how we solved it? I'm gonna skip 12 and just do 14. They're the exact same question. The numbers are just, the question is nicer in 14. Okay, for question 13, the protein that you have just isolated is unstable. It decomposes through a first order process with K equal to 0.02 minutes to -1. How long will it take for 99% of a 1.6 mil sample of the protein with initial concentration of 87 micromolar to decompose? This is. What do we have to do here? Yep, you have to find the remaining concentration. Does the 1.6 mils matter? It does not, right? If we are assuming 99%, you can say that you started off with 100 and you have 99% of that decomposed, so you have how much left over? You have 1% left, okay? What is our integrated rate law for a first order reaction? With the one that will be easiest to solve this question. To the negative KT. Yep. So you can use this one. I actually prefer your ln AT is equal to negative KT minus ln minus plus ln. I believe those are the two forms, if I'm not mistaken. Either one of these will work for this one. I prefer to work in the straight line plot, so that integrated with the ln, but you are more than welcome to do the AT one as well. Any questions so far on what we're doing? Okay, I'm gonna solve using the ln just because I've done that before. So your ln AT, what is our concentration of AT? 1%, so that's gonna be 0.01, right? We can't use percent, so we can just use 0.01. You could say also 1, and then you can start off with 100. That's fine too. But 0.01 is assuming that you started off with 1, and then that fun stuff there. Do we know K? What is it? What's our units? Yep, 1/min. Do we know what T is? Nope, that's going to be X. And then I didn't give myself enough space. What is our concentration of A0? It would be 1. Okay, so again, this just becomes solving for X. We're going to subtract ln of 1 from both sides. So once we get this, we can divide by that negative 0.02.
So I don't get the concentration. I had to get 0.01.
Yep. So we're saying that 99% of your initial protein stock is decaying or has decayed, right? So if we assume that we started off with 100% and 99% decayed, how much is left over? Right, we're left with 1%. So this is our initial,
Okay.
and this is our final.
Oh, okay.
Right, so you can
So
either,
That's just to trip you up to 87.
yes,
And
the
you could
80s.
use the FP gauge, you could-
Yes,
Okay.
yep. You could use your 87 micromolar to find what 99% of 99% of that 87 micromolar is, but you don't need that, and you don't need your 1.6 mils. Because whatever you find, it'll be 100% and 1% left over, so you can just cut out the middleman and just do 101.
The concentration can go under like.
Yeah, so I just converted mine out of percentage. So instead of having 100%, I have 1 and 0.01, but you could also have used 101.
Oh.
Right, you could have plugged in 100 here and 1 here, and that would have been the same. I don't think so. That would seem rude. And at the end of the day, it's just going to come down to 100% and 1%. So I think it would be fine to just use your percentages. Okay, so I get that T is 230. Does that mean let's answer choice C? Why not? Yes, our units are in minutes. So I would look at that and say it's more than 230 seconds. It's more than 0.05 seconds. And it's more than 0.5 minutes. Because we're already in minutes, and it's not 86 minutes. So it's probably going to be the 3.8 hours. But I would probably prove that to myself and say that 1 hour is 60 minutes, and that gets you to 3.8 hours. Yes. I did the ln of 0.01 divided by 1. So this here comes ln 0.01 over 1. It's log math here again. So whenever you have ln of 0.01 minus ln of 1, it looks like ln. And when you're subtracting, then they divide. So then it becomes and then because they're both ln functions, then you can say that this is ln. And you can plug that into your calculator. Yes. How did I do that? Because my units of t are in minutes. So when I get t is equal to 230, it's not in seconds. And none of the minutes answers matches 230. So just to prove to myself that it's the hours. Yes. Yep. Yes. 14 is similar to 12. Yep. I believe it's the same answer for. Yeah, 12 and 14 are the exact same question, just asked slightly different. Yeah, I'll show you 14 and I'll show you how it's different from 12. Any questions on 13? Feel good about this one? Right, so you could do this again and you can say, okay, how long would it take for 85% of my stuff to decay, right? You can prove to yourself that you can find that t as well. You could also say, okay, I have 100% after, right? This is 3.8 hours. After 1 hour, how much is left over? And you can find that percentage there as well. Nope. Yeah, so you could, as long as it comes out to, so I was just saying, like, if you wanted to try this type of problem again, switch how much is decaying. So say 85 is only left over. Yeah, yep. Yes. Yes. I made ATS 0.01 and I made a 0.1. Because that would be 100% and then 1%. Yeah.
So volume almost never matters in reaction rates.
Yeah, pretty much. Yeah, it would only matter if you're given the moles of something and then and then the volume, and you need to find concentration. For rates, we mostly work in units of concentration. Yep. I'm sorry, we work in units of concentration. Anything else on 13? Okay, question 14. At 650 Kelvin, the rate constant for a reaction is that, while at 700 K, the rate constant is that. What is the activation energy for the reaction in kilojoules per mole? What do we need to use for this one? Yeah, the fancy formula that looks like the combined one that we just used. Can someone give me that formula?
Equal to the activation energy over constant R.
Yep.
Okay.
I was just saying A. Yep.
Yeah, activation energy over R. Open parentheses of 1 over T1.
T1.
1.
2.
Okay. Minus 1 over T1.
Yes.
Okay.
Yep.
I was questioning that because I had it to minus T1 and the row next got it minus T1 and I was like, okay.
Yep. So it doesn't really matter if it's T1, T2, right? This, you could have also said ln of K2 over K1 is equal to EA over R times 1 over T1 over T2.
Yeah.
It does not matter as long as, right, top and bottom is different than left and right.
Yeah.
Right, your top and right should match, and then, I'm sorry, that's probably different for you. Your top and right should match, and then your bottom and left should match. Right, you need to go 1, 2, 2, 1, or 2, 1, 1, 2. Either one does not matter. Okay. mean, if you want, it's mostly gonna be this, I think. I have the important creations. I just don't remember it off the top of my head. I'm mostly used with this one, just the regular Arrhenius. So this regular Arrhenius you can solve for. What it involves is, I believe, subtraction and also taking ln functions, which you can do. It just becomes a lot of log math afterwards. So I would just recommend memorizing the both. Yeah. I don't think you'll have to use the K one, but if you need one equation, then it's like, or you only have one rate constant, then that's works for you there. Alrighty. For our temperatures, what unit do we need to be in? We need to be in Kelvin. Are we in Kelvin? We're good to go. What is our R?
0.032.
8.314 for this one. Yep. R here is 8.314 because what's the units on 8.314? It's joules per mole Kelvin, right? We need to be in energy. The other one's in your liters per ATM.
Is it in kilojoules?
So you can either change your rate constant to kilojoules or your activation energy to kilojoule or to joules. I would, in this case, probably solve for it in joules and then convert it to kilojoules at the end. Okay, so for 650 Kelvin, is this T1 or T2? T1. It doesn't actually matter if you call it T1 or T2. You just need to match it. And so that 2.15, what is that going to be? K1. Your 700 Kelvin is what? T2. And then your 239 is what? This is K2. Okay, so now you have your question annotated and we can plug that into our equation. And then it again just kind of comes down to boiling down to solving for that EA. So K1 is 2.15 times 10 to the negative 8 over 2.39 times 10 to the negative 7. We do not know EA, but we know 8.314. T2 is 700. And T1 is 650. I would solve for your ln. I would be mindful of your parentheses as well. And then I would do your 1 over 700 minus 1 over 650. And then I would take that number and divide it by the 8.314. So then you can divide by that number by the ln you solved. So EA comes out to be 182.213.28. What is our units on EA? It's joules per mole. So how do we get to kilojoules? Divide by 1,000. And so we're going to end up with 182 kilojoules. What questions do we have here? This one feel okay? I believe so. Yeah, it's given to you at the top of the homework, so it should be at the top of your exam as well.
Because I saw the R is equal to 0.082 ATM times Q.
Yep, and it also says equal to 8.314 right after.
Oh, yeah, sure, okay, I see. It's just how the.
Mhm. So I did my temperatures first, subtracted those, and then divided by the 8.314. Oh. Yep, so you just want to make sure you have extra parentheses. So in your do you have like one of these guys? Yeah, similar. So I would just make sure that you have like in your calculator, it'll say ln, and then you want extra parentheses of 2.15 times 10 to negative 8. And then divided by 2.39 times 10 to negative 7. That also gets parentheses, and then you close your big parentheses. So then that entire thing being divided is in your ln function. Yeah, the entire fraction needs to be in the ln function. Yep.
And then could you, like, what you just did, but with the temperature and.
Mhm. Yep. So in my calculator, I did 1/700 minus 1/650. Got that number. So this was number. And then I did this divided by 8.314. Okay, this equals this number right here. So then I typed in negative 2.4084 divided by answer. And then that should give you that 1.8. Sometimes plugging into the calculator is the hardest part. And trust me, I've had a lot of practice doing these problems, you know. Okay. To look back at question 12, right, we're saying the rate order for a first order reaction was measured at 2 different temperatures. What is the activation energy? Those numbers given, 2.15 and 2.39, are almost the same as the first of what we were just given. You're just given 377 and 427, which if you solve for in Kelvin, is 650 and 700. So this one's just the extra step of making sure you put it into Kelvin first. So you can go back and try 12 to see if you get the same answer.
This is not related to the homework, but this is osmotic pressure on the test. That's just solve like the ideal test solution, right?
Yes, it's essentially the same. It just uses the pi instead of pressure. Yep.
And that like doesn't make a difference in how to solve it.
Nope. I actually did that last week in this session. So if you look at the video, I go over that question from like the homework that we skipped last time. Yep.
For the rate for the pi equals NRT, is that the 0.08?
The R for that one, yeah, that's 0.08. Yep.
And then also the one behind you, why is it 12 again? Because it's squared?
Yes.
Okay,
Yep.
so it's just supposed to be concentration.
Yes. Yep. In like how, I guess. Okay, so. Yep. So if we're given something, what are those? So this one we have a reaction has the following graphs. What is the rate? Not rate. What is the rate? Why is it first order? So we get a straight line plot for ln concentration versus time. And that's what's going to tell you that it's first order, right? If it was a straight line for the A over T, then it would be 0th order. If it was 1 over T straight line, then it would be second order. Right, so if it was I don't know what it looks like for this one. It looks like that for that one. What order is this one? It would be second, right? The straight line for the 1 over A is the one that gives you a straight line plot. And so this one would mean the rate order. Yes. Yep. Does that help your question a little bit? Yes.
So it's first order, like whenever you manipulate your data, that's the only one that has a negative slope, right? Everything else will be positive.
I believe so. Yep. Yep. I'll post these two. The Zoom is still recording, so. And then anyone else need this for right now? I did go through important equations. Is this something we want to talk about? I can just post them, whatever's easier.
Yeah.
Am I allowed to do that if you're supposed to memorize them?
We know what's next.
It's-
I mean, I don't have to take a photo now.
I mean, so I'll just like write this on the Zoom. So I guess I'll just scroll through and you can go back and pause it later. Right. So just what I've briefly looked at, right. We have your general case rate of reaction. Right. And we want to know that rate of reaction is defined as what? Dx over dt, right? That's really the most important thing to remember. For first order reaction, we have our like 2 equations that you can work with, but your ln over at is what gives your straight line plot. So if you're given something and it graphs and it's a straight line with an ln of at or ln of concentration with t on the x-axis, that means it's going to be first order. Do you have to know half-life? Did we talk about that? Yes. So there's your half-life equation. That'll be constant for any first order reaction. It'll always be that 0 over 693 divided by the rate law. It's the ln of 2. And so that's just a constant number. I don't believe that like this is actually given, but it's either the ln of 2 or the 0.693. And then your rate law expression is that. For second order, again, your straight line plot is that 1 over A times concentration, or 1 over A concentration. So like we saw just a second ago, your half-life is this here where your T1/2 is dependent on the concentration this time, right? The first order was not dependent on concentration. Second order is dependent for your half-life. And then same thing, rate law expression. And then 0 order reaction, we have your straight line plot is going to be that negative KT. It's just dependent on concentration. So this straight line would be A over T, and it would just look like this. Okay. And then your half-life is again dependent on that initial concentration, but you're just dividing it by how many half-lives have happened. And then your rate law expression is just here with no extra concentration involved. Say it again. Yeah. Right. So it's like, it's just dividing by 2 every time, depending on how fast the reaction is happening for 0th order, right? So we have, yeah, just explain what it is.
The rate law and zero.
I don't think it should be. I might have just hit my screen an extra time. It should just be okay. Right, because this is, oh, I'm sorry, it should be negative. Because it's like the rate law expression defined as the dx over dt, and so your reactant will be negative. Yep. And I believe these are just in your notes if you look at like 0, 1st, and 2nd, just to make sure that I'm telling you the right things. I was watching football and crying when this was happening, so it's fine. So then your Arrhenius equation, you have that one singular one where your rate constant is dependent on A, and then that EA, but you don't technically really have to solve for it. Or if you don't have to derive the one below it where you have the 2, but I would know your Arrhenius equation just in case he's looking for an activation energy at a certain temperature given a rate. And then your combined Arrhenius, and then the straight line for that Arrhenius, I think is what's most important. Yeah.
Just for you, if you were to do the first one, how do you do the log? Like if you're trying to find P.
Yep.
How do you, I forgot how to do log.
Yep. So we have K is equal to AE over EA over RT. So I would divide by A first. So you have K over A is equal to E to the negative EA over RT. So in order to get rid of that exponent function, you need to take the ln. So this becomes ln and ln. This cancels out. So you have ln of K over A is equal to negative EA over RT. And then, so if you, so if you want, if we're saying we're solving for EA, then you could say you have RT times the ln of K over A is equal to negative EA divided by -1.
So you don't have to use log, you can use.
Yep. Yep. So then
The opposite, like if you're dividing by E, that would be technically.
the ln. Yep. If you use log here to cancel out the E, it'll not work. Yep.
What is log?
Log is just for if you don't have an exponent. So that's like if we were looking at your exponents for your rates given a table.
Yeah.
If you can't tell what that exponent is, then you use a log function because it's just a base 10.
You know, okay.
Yep. And there's no like exponent or that no E function in there. So then you don't need to use the natural log to get rid of the exponential. Yep. This is just to tell you, right? You could say that if you have a graph like this, it would be y mx plus b. Sorry, b. So then you would have this graph here, and then so you can say what's the slope based off of your ln k and your 1 over t. You can use this to find what your slope is. You can find the activation energy from the slope because R is a constant. If you really want to derive the straight line plot, you could take your derived straight line plot, and then that's how you get to the combined if you subtract the 2. So you take one straight line plot minus the other straight line plot. But this step here is where you would deviate to try and solve for ln of A. I'll show you just real quick. Yeah, A is the Arrhenius constant, I think. But it would be given to you in the question. It's dependent on the reaction. So if you have ln of K over A is equal to negative EA over RT, again, this comes into exponent math. So this means ln of K minus ln of A is equal to negative EA over RT, right? They're being divided. So then you can add them. And so you get ln K is equal to negative EA over RT plus ln A. And then that matches this guy up here. And then you're happy with yourself because you can derive equations. That's where that comes from. And I don't think you need to know it if you just memorize them. But I don't want to tell you to memorize something else if you don't have to. Anything else? On the practice, yeah. I don't think I downloaded that yet. So we'll go to Canvas. Okay, question 1, you said. So regardless of the bond breaking always releases energy. True or false?
Yeah.
I don't know as well.
On break.
No, not really.
No, it takes energy, so it's all.
Yes, this is false. All,
Wait, to make bonds?
yep, so all bond breakage requires energy. All bond formation releases energy.
Oh, so like if gases are condensing to a liquid, maybe they're extra for like moving slower to like collide.
Yep. Right, so if we're looking at, right, a liquid to a solid, we're getting more of those intermolecular forces, we're forming bonds. So since we're forming bonds, that is releasing energy, causing it to be colder in the system, so then we get ice.
And if there's too much kinetic energy, the effect of the intermolecular bonds are big enough to give us the invasion.
Yeah, so if there's like too much kinetic energy, then those intermolecular forces don't matter because they're moving too fast to create those intermolecular forces. Questions on 1? The units associated with the extent of the reaction is. Question 6.
Yeah, axis.
It's a math.
It's a concept, it's not real.
So the key is saying that dx over dt is concentration.
Yes.
Yep.
Wait,
I thought that's what he said.
yeah.
Only for X.
Yep.
doesn't that make it useless?
So if it's,
Asking for, like, BX.
yes, it's asking for x here. What does the brackets mean? Concentration. So anytime you're in these brackets, this is concentration.
Is it because it's a concentration over time thing?
Yes. So this is where that concentration over time comes into, but just the units associated with the extent of the reaction, x, not dx over dt, but just that x is the concentration.
So extent of the reaction is always the DXCT?
The extent of the reaction is dx over dt. X is in concentration units. Yes. Yes.
So with both of those, okay, so but for X by itself, is units? Wait, why do you say X is units?
I think, yeah, my understanding is like, 2A plus B. There, C plus X.
Yes. Yes. When it is in 2a plus b goes to 2c plus x, unitless, because we don't have
Oh,
units in the reaction. Right here, unitless.
oh, yeah.
Right here, this is where it's unitless.
Oh,
But in terms of dx over dt finding a rate, then it's concentration for x over some time.
so it's more concentration units than units.
I would say yes. We're just saying it acts like a product. This is where it would look like, right, kind of thing.
That's the wrong thing about that.
Question?
Can you go back?
Are you going to release the justification for the practice
Yeah,
at some point?
at some point we'll do them. I present in group meeting on Friday and I have 4 slides done and one of them's my title slide. So I just gotta make sure I do that a little bit before I do this. But it will be released before tomorrow night.
Oh,
Yeah.
cool. Yeah, great, quick question.
Let me finish this.
Can you go to the one where it's like, if one, or one and two are correct?
Yes.
Can you go, I think it was-
Question 7. Yes.
Yeah, seven. So I'm just confused on the first one.
Yep.
So the rate on the first quarter, I have to change over.
Yep. So
What equation am I looking at there?
So you just want it, it's more not the equation and more of the concept of what a first order reaction is, and then the graph associated with it.
Just change, yeah, that's just the definition.
That's yes, right? So for a first order reaction, right, we said that this is logarithmic. So it has that right slopey thing here. So it's going to have a faster decrease in the beginning than at the end, right? Not to the extent of a second order reaction, but the more stuff you have in the beginning, the faster it will happen because it's for a reactant.
Okay.
And then over time, we're using that reactant to get two products.
Okay.
And so we have less of that reactant to react. Therefore, less collisions are happening, less reaction is happening.
So that's why for zero, since it's a straight line,
Yes,
it's constant, so it doesn't change.
it doesn't change because it has no dependence on what that concentration is as the reaction is happening.
What is the axis for that one?
This one would be concentration of A over T. Yep. Say it again. It would, yes, if this was said second order, it's still a true statement because we're still dependent on that concentration. Yep, but if it was a first order reaction, or I'm sorry, if it was a 0th order reaction, then this statement would be false.
But then the temp one, that's just always false, because temperature doesn't really have to be long. I think the reason why it's false is because of the rate constant.
Yes, the rate constant of a first order reaction will change with time at the same temp. At a certain temperature, the rate constant is staying the same. K will be K at that temperature. If you increase the temperature, then K changes, but at a certain temp, K is not changing. Right, this rate constant, this is K, this rate, this is R.
Oh, rate constant. Oh, okay, that makes.
Yes.
Rate
Yep.
constant,
But constant will never change.
Yeah, constant will not change. If it says the rate constant of a first order reaction will change with time at different temperatures,
that's true.
then it would become true, I think, because, no. Because over time, with time makes it false. If it says the rate constant of a first order reaction will change at different temperatures, then it becomes a true statement.
Okay, so rate constant has nothing to do with time.
No. Yes, yep. Right, if you have a higher temperature, then your rate is going to be happening, or then your rate will be faster, so your K will be higher. Yes.
I got thrown off by like different manipulative graphs and looking at every order is on the same like A versus P. But just to find a straight line and like figure out which one it is, to make it easy for yourself.
Yep.
You do the ln or 1 over.
Yes, yep. So you can always graph something with a concentration over time. But in order to find the straight line plot, that's when you have to take those concentrations and either do the ln function or do the 1 over concentration function. Do we feel better?
Yeah.
Okay.
So it's like,
We're getting into my favorite stuff of the semester. So
really helpful.
okay, awesome. So I will release, I guess, this once we finish the Zoom, I'll put that on the internet. You can access that. I'll just do a little announcement like last time. And then once I work through the practice exam, then I will put those answers up as well. Anything else you want to see from me before Friday? For the practice exam? Let me go look. I needed to find a timer to form. Wow, that's a name. Interface process. I would have to do this to find out if there's actually a typo.
Basically, I thought. that's. And the key says it's also.
yeah, he probably just made a typo then, because it says it's a first order process, so it should be molars over second. No, that's true. If a first order, then it should have no units of concentration. Yes. Yeah, because if we're looking at, right, this one here, this is a second order reaction. But if we had a first order reaction. Then units for R are 1/millimolar, I'm sorry, 1/seconds. And then, sorry, no, this, and then units for K is 1/seconds. Yep. Yep, yep. Good. Okay, 2 hours, ladies and gentlemen. Awesome job. I should be available by email if you need me at some point. Just give me like 24 hours to respond. I'm done with group meeting by 10:30 on Friday. So your last minute questions I will be able to handle. Do you want it?
Oh, I'm just.
I mean, I can, it's only an hour. Was that helpful last time?
Yeah.
Yes, okay. Okay, I can do I'll again 8:30 to 9:30, 1 hour for cutoff. People mostly had just asked about the practice questions, or if they didn't, my Zoom did not work last time, so they might have asked a couple questions about the homework again. But it's just like last minute questions, last minute anything. I just do it on Zoom. I'll send out a link. Yep. Once I post this, I'll also post a link for tomorrow as well.
Thank you.
Yep. Thank y'all. Thank you. I'm gonna need it.